The solution to this problem is to build what's called a spanning tree. The spanning tree permits loop-free forwarding on an underlying network topology that may contain cycles. Suppose we have the following underlying network topology of switches. Ultimately, what we'd like to compute is a spanning tree, which is a subgraph that covers all the vertices in the graph but contains no cycles. For example, the connection of links highlighted in blue forms a spanning tree. It's a subgraph. It covers every vertex in the graph, but it doesn't have any cycles. To avoid forwarding frames in loops, instead of forwarding a frame on every output port, a switch will only forward a frame on the output ports that are members of the underlying spanning tree. Links that are not in the spanning tree do not forward the frames. So you can see that even if we have a packet that needs to be broadcast, then simply broadcasting the packet along the edges in the spanning tree is sufficient to ensure that every host in the network receives the frame, and yet no forwarding loops exist. So how do we construct a spanning tree? The first step is to elect a root for the tree. The root of the tree can be arbitrary, but it is typically something like the switch with the smallest switch identifier. Next, each switch needs to simply exclude links if they are not on the shortest path to the root, or if they're the same distance from the root as some other link but have a higher identifier. Let's take an example. So this switch here needs to figure out which of its three interfaces are part of the spanning tree. The middle interface is on a shortest path to the root. It is one hop away. Therefore, that link should not be excluded. However, this interface is 3 hops away, and this interface is 2 hops away. Therefore, both of those links are excluded from the spanning tree. We can apply a similar algorithm at each of the switches. Let's take a look at this switch. Here we have a link that's 1 hop away, so that becomes part of the spanning tree. And we have another link that is 2 hops away from the root. So this link is excluded from the spanning tree as well. You can repeat this process at every switch, and ultimately you'll end up with the spanning tree. So initially, every switch thinks it's the root, and it announces itself as the root. Switches then update their view of the root when receiving messages from other switches claiming that other switches are the root. Upon receiving a message from another switch, it checks the root ID of the other switch's announcement. And if the ID of the message that it hears from another switch is smaller, it updates its view of the root so that it views the other switch as the root. Switches then compute their distance from that new root, adding 1 to the distance received from any neighbor claiming that particular switch as the root.